Hello and welcome. In this lecture we will be learning about resistors, Ohm's law, and power. Before we begin, you may notice that there's some changes made to this video. First is that I've decided to exclude my webcam video and also to start doing voiceovers. And the overall purpose of doing this is to just make the videos more efficient and be able to reduce the delays that are introduced by not editing the video. So it'll be more edited from now on, and the purpose is just to make it more efficient. Now, this is a very important lecture because we're talking about some of the more physical underlying concepts, such as resistor. In this case, it's going to be resistor models, Ohm's law, power, and a quiz that you should definitely try to take. More about more abstract concepts and circuit analysis concepts. So what do we know about resistors? We know that they're used mainly to limit current flow, to set voltage levels, and they're measured in ohms. Now, an ideal resistor, when you apply a voltage across its terminals, it will give you a certain current. And in this case, we have a temperature-dependent model. And if you look at the IV characteristics of a resistor, ideally you have a straight line, but then in reality you would have a more curved line, as such, as shown here. Now, let's look at the temperature-dependent model. Let's say that we have some R0 being 10 ohms, T0 being room temperature, roughly 25 degrees Celsius, A being a coefficient of a temperature coefficient of 1 ohm per degree C, and T being a final temperature of 100, which is beyond the boiling point of water, and R equivalent at 125 degrees C being 10 ohms plus 1 over 1 ohm per degree C times the quantity 125 minus 25. So overall we get an R equivalent of 10 or 110 ohms. This example will just have a temperature dependent model could predict the resistance value at a higher temperature than the room temperature. Now another model is the basic model is shown here, and if you were to do RF or anything more complicated than that requires a better model, you would use this sort of a more complex model. And you can see we have parasitics all over the place. We have parasitic capacitance and inductances. But what we'll be mainly using is the ideal resistor model that I've circled in green over here. So we won't make more advanced models in this course. We have enough to learn as is. Now, talking about Ohm's law, we have this very famous relationship V equals IR, and it's a very idealistic, simple relationship that applies for most of our circuits. Now, what it tells us is that if you have a resistor and you apply a certain voltage across its terminals, being Vs, that voltage drop Vs will fall across the resistor, and it will give us a certain current that is predicted by this relationship, which is called Ohm's law. Now, if you look at the circuit here in figure 1, you can see that by applying a voltage Vs, that voltage will fall across R in the given configuration with that polarity, and assuming that there's no loss in wires, the entire voltage will fall across that resistor and produce a current I. In figure 2, we can see that if current I is forced through the resistor, giving us also voltage drop Vs. Looking at this graph, you can see that resistance is represented by the slope of the line. So for example, if you have R1, R0, and R2, you can see that R1 is greater than both R0 and R0 is greater than R2. And you can kind of make sense of it saying that, okay, if for example R1, a small amount of current will give us a large voltage, which means there's a huge resistance. That's just one quick example. To put some numbers into this, you will see that example 1 says find I if voltage is 120 volts and R is 10 ohms. In this case, we apply Ohm's law and solve for I, plug in the numbers, and we get 12 amps. In the other example, it tells us to find voltage if we have the current and the resistance, and in this case, we also plug in the numbers and find 15 volts. Now let's move on to power and talk about the fact that voltage and current don't tell us the whole story. Rate of energy transfer is also important to know. So if you think of a 60 watt light bulb and a 100 watt light bulb, you clearly see that there's a qualitative difference in that the 100 watt light bulb gives you more bright light. Now, 1 watt is defined as 1 joule per 1 second, and using that we can say that P is equal to dW dt, or the rate of change of energy per time, which you can rewrite as dt, and that's an algebraic manipulation there. Now, if you recognize those quantities, those are voltages and currents, so then this tells us the generalized power V times I, or I times V. Now let's look at some useful relations. So V equals IR, another form of that is I equals V, is P is equal to VI. So if we plug in equation 1 to equation 3, we get P is equal to I times, which is equation 1, plugged in to equation 3, and there's V times I. So I times R times I gives us I squared R, which is a famous power dissipation equation for resistance. The other equation is we plug in 2 to 3, and we see that that's going to give us V over R times V. That gives us V squared over R, and usually the current through the resistance, and you just know the voltage and the resistance. So now let's talk about passive sign convention. So this convention takes into account voltage polarity and direction of current. So say you know that a current is flowing from plus to minus terminals of a given element. You would say that that element is dissipating power, and if the current flows from the minus to the plus of that element, you would say that it is supplying power. Now, keep in mind that this is conventional current, so it's you can think of it as a positive charge flowing, or electrons flowing from the opposite direction. Now, to think about this more clearly, falling down on from a hill and hitting a bottle, the ball here being the positive charge, and if it goes from higher potential to a lower potential, it has dissipated energy. It uses up some energy to crash into a bottle. Now, if you were to move the ball from a lower potential to a higher potential, you would need to supply energy to it, so you would lose energy. You would have a minus sign, if you will, and you would raise the ball from a lower potential to a higher potential. That's a very loose analogy, but it will help us think about this. On to talking about conservation of energy. In physics, we know that energy cannot be created nor destroyed, but only transferred. In the context of circuit analysis, energy sourced by an element is dissipated by other elements. So at all times, at all t is equal to 0. And in this case, I've written it out just to show an example here. So some powers are sum up to 0 in a given circuit. So let's now move on to the quiz. We should be ready by now to tackle this. So in problem 1, you have to calculate the power dissipated or absorbed by each element in the circuit. A total of 10 amps flows from a 12-volt source through some passive devices, and we have a dependent current source here, which has a current I over 5, and the 10 amps that I discussed here. Now, you should be able to find the power dissipated and absorbed by each of these elements correspondingly. Whichever one absorbs or dissipates power, you should know. In this other problem, we have a mysterious element with the given IV current and voltage equations here. For part A, we have to find the charge transferred into the element for t equals 0 to t equals 2 seconds. Part B, we should find the power absorbed. For part C, we should find the energy transferred to the element from t equals 0 to t equals 3 seconds. Okay, so now let's stop the video and give it a try. Okay, I tried it. Power 1 is going to be negative 10 amps times 12 volts, because we have 10 amps flowing from the minus to the plus of the supply. So we get negative 120 watts. Then for power 2, we have 10 amps flowing from plus to minus of the element, which is plus 20 watts. For elements designated by P3 and P4, we can see that they share a node, so the voltage across them is going to be the same. So V3 equals V4. Now, we have to then find the current through the dependent current source, which is I over 5. So we're going to have, since it goes from negative to positive, we're going to negative 10 amps over 5 multiplied by 10 volts, which is negative 2 amps times 10, which is negative 20 watts. Then then we can see from the left to the middle node, and then 2 amps from the right to the middle node. That gives us a sum of 12 amps flowing down through the element given by P3. So P3 will be 12 amps since it's going positive 12 amps since it's going from the plus to minus. So that's going to be 120 watts. So we should check that this meets the criterion for conservation of energy. So writing all these terms out, we get negative 120 watts plus 20 watts plus 120 watts minus 20 watts. So the sum is indeed 0, and we see that energy is conserved. Additionally, we see that the energy supplied from the 12 volt supply and also the dependent current source. Now looking at problem 2, then we see that we should probably write out the current and voltage down here. So for part A, the current is given as 10 milliamps times e to the minus 2. The voltage is given as 5 di dt. So the derivative of current with respect to time is going to be 2 times e to the minus 2t. That's just rules of calculus. That's going to be in millivolts. The final answer there is going to be 5 times 10 times minus 2, which is negative 100 millivolts times e to the minus 2t. The current is dq dt, if you recall. So if you take the integral on both sides with respect to time, you get q of t. Now recall that if you take the integral itself, you're going to have also a unit introduced, a unit of seconds, since we have dt here. So at the end, we should remember that it's going to be over seconds, which is amps, times seconds, which is coulombs. So here we see that the answer here is going to be 10 milliamps over negative 2, since the integral of e to the minus 2t over negative 2. So I flip the bounds here and get rid of that negative. So from 0 to 2, instead it's going to be 2 to 0. And when we plug those numbers in, we get 5 milli coulombs times 1 minus e to 4.91 millicoulombs. Now for part B, we have to find the power absorbed. So let's just go ahead and first and also the voltage. And what we need to do according to the generalized power law is to multiply these two quantities together and find the power at all times t. So at all t, we're going to have I times V, which is 10 milliamps times negative 100 millivolts, e to the minus 2t times e to the minus 2t, which is negative 1000 times 10 to the minus 6 watts times e to the minus 4t. Now the 1000 is part of the 10 to the minus 6, specifically it will cancel out 10 to the minus 3, and you'll get negative 1 milliwatt times e to the minus 4t. So that's our power. Now, although you're not asked, let's just go ahead and graph it just to see what these waveforms look like. So for the voltage, what you're going to 0 is negative 100 millivolts times e to the minus 2 times 0, which is negative 100 millivolts. And as the limit as t approaches infinity, so as t grows very large, we see that we have 0. And I rewrote e to the minus 2t as 1 over e to the 2t. So that's our waveform. The decay rate is negative 2, which is in the exponent of the exponential function. And if you draw the current, it's going to be similar, but it's a positive number. So now power, it's going to be the multiplication of the two, so it's going to be starting at negative 1 milliwatt, and it will decay at twice the rate of each of the individual functions. So it's going to be dying away a bit faster, as you can see here in the green. So that is our power. So it starts negatively and it goes to 0. So the point here is graph when possible, just to do a sanity check and see that things make sense. So in this case, the power is being absorbed for t equal t approaching infinity, because when t is greater than 0, the power becomes less and less negative and goes towards 0. And if you want to take a look at the schematic of what we talked about, the source and the mysterious element, if you flip the mysterious element around to have the grounds tied up this way and perform a Kirchhoff's voltage law, which we'll discuss later more, but in this case you sum up the voltages according to their polarities. So you start from V mysterious, you see the negative side first. If you start from the top, you see the negative to positive, then the positive to negative of V of t. You sum those up and they should equal 0, again according to the conservation of energy, but applied differently here for KVL. And they have to be the same, and the currents also have to be the same since they're in series. Now going up to part C, then power is given as dW with respect to time. You get that the energy transfer from t equals 0 to 3 is the integral of the power given here. And when you factor out the negative 1 milliwatts and take the integral, you have a negative 4 introduced at the bottom there. You cancel the negatives and you take the integral from 0 to 3, and e to the minus 4 times 3 and minus e to the 0, which is 1. Now e to the minus 12 is a pretty large number. It's a little over 160,000. Multiplied by 4 is even bigger, so that's a roughly 0. So we can pretty much neglect that and only stick with the negative 1/4 of a milliwatt there. In this case, we need to also remember that we took an integral with respect to time, so a unit of seconds. So you have joules over second times second, and that gives you a joules, millijoules there. So the total energy given to that was negative 1/4 of a millijoule. That's it for this lecture, and I'll see you in the next video.